You're listening to the AI Podcast. I'm Sam, and with me is Nina. Today we're unpacking a new Google DeepMind white paper titled AlphaEvolve, a coding agent for scientific and algorithmic discovery.
Hey Sam, I skimmed it, but I'd love the plain English version first.
Sure. The headline is straightforward. AlphaEvolve is an agent that has large language models write and rewrite code, test the results with automatic evaluators, keep what works, and iterate. With that loop, it discovered provably correct algorithms. The standout example is multiplying two 4x4 complex matrices using 48 scalar multiplications. That's the first improvement in this setting since Strassen's result 56 years ago. It also delivered practical wins inside Google's stack.
Wow, that's a lot already. When you say practical wins, what kind of improvements are we talking about?
Three clear ones. First, a data center scheduling heuristic that consistently recovers about 0.7% of fleet-wide compute after rollout. Second, a tiling heuristic for a key matrix multiplication kernel used in Gemini training, giving around a 23% average kernel speedup and about a 1% reduction in overall training time. Third, direct compiler-level edits around a flash attention configuration that sped up the kernel by up to 32%, with about 15% gains in pre- and post-processing steps.
Got it. Before we go deeper, who wrote the paper?
It's an 18-author team from Google DeepMind. The author list includes Alexander Novikov, Ngân, Marvin Eisenberger, Emilien Dupont, Po-Sen Huang, Zsolt Wagner, Sergey Shirobokov, Borislav Kozlovskii, Francisco Ruiz, Abbas Mehrabian, Pawan Kumar, Abigail C., Swarat Chaudhuri, George Holland, Alex Davies, Sebastian Nowozin, Pushmeet Kohli, and Matej. The PDF lists Google DeepMind as the affiliation and notes equal contributions for several authors. Corresponding authors are Matej, Alexander Novikov, and Pushmeet Kohli.
Thanks. So what problem are they really tackling here?
They're aiming at scientific and algorithmic discovery where you can grade candidate ideas automatically. In those domains, an evaluator can say whether a proposed program is correct and how good it is. That creates a safe loop. The model proposes code changes, the evaluator scores them, and only improvements survive.
Right, so the computer can grade its own homework. Haven't we seen LLMs evolve code before, though?
We have, but prior systems were narrower. FunSearch evolved single functions with very fast evaluators. AlphaTensor specialized in matrix multiplication. AlphaEvolve expands the scope. It can evolve multi-function, multi-file codebases, use stronger base models, and tolerate longer evaluations, including runs on accelerators. It also optimizes multiple metrics when needed.
Okay, how does AlphaEvolve actually operate?
A user provides a task description, a working code base, and an evaluate function that returns numeric metrics. AlphaEvolve samples rich prompts that include prior programs and results, asks an ensemble of models to propose code diffs, applies those diffs, runs the evaluators, and stores outcomes in a program database. High-performing and diverse programs become the parents for the next round.
And where did they test it?
Across three tracks. First, algorithm discovery for matrix multiplication, where AlphaEvolve improves the state-of-the-art on 14 targets. Second, a suite of over 50 open math problems with machine-checkable criteria. Third, production engineering at Google, data center scheduling, kernel engineering for Gemini, compiler-level optimization of attention, and even RTL edits for TPUs.
Let's unpack the math result. Why is 48 multiplications for 4x4 complex matrices important?
The number of scalar multiplications is the key score. For 4x4 complex matrices, the long-standing benchmark derived from Strassen's approach was 49. Dropping to 48 breaks a decades-old barrier. The team verifies exactness and provides code to check the constructions.
And the broader math suite, how did it do there?
They report matching the best-known results on roughly 3/4 of the problems and improving about 1/5. One example is the kissing number in 11 dimensions, where they raise the lower bound to 593. They also include a notebook so others can inspect and verify the constructions.
Let's shift to the production results. The scheduling gain, 0.7%, sounds small. Is that actually meaningful?
At Google scale, it's substantial. The heuristic ranks candidate machines for each job using simple functions of CPU and memory residuals. They tested in simulation on historical snapshots, then deployed fleet-wide. Post-deployment measurements show the average recovery is about 0.7% of compute that would otherwise be stranded.
Okay, and the kernel engineering piece?
They evolved a tiling heuristic for a matrix multiplication kernel used in Gemini training. The goal was to minimize runtime across many input shapes on real TPUs. The discovered heuristic yields around a 23% average kernel speedup and trims overall training time by about 1%. It also shortened the engineering loop from months to days.
And the compiler workaround attention?
They optimized compiler-generated intermediate representations for a flash attention configuration, plus the surrounding pre- and post-processing. Even in that already optimized setting, they report up to a 32% speedup for the attention kernel and about 15% for the surrounding steps with checks for numerical correctness.
That's a wide range of applications. What's the author's main takeaway?
Let models be creative, but anchor the search with hard evaluators and an evolutionary memory. That combination finds improvements people might not try, and it filters out fragile ideas quickly because everything is checked by code.
All right, let me ask the skeptical questions. What should listeners keep in mind?
First, it's a white paper, not yet peer-reviewed. Second, several results depend on Google's internal simulators and infrastructure, so full external replication is not straightforward right now. Third, AlphaEvolve needs machine-grade evaluators, so domains that require physical experiments or subjective judgments remain out of scope.
Makes sense. Any clear next steps the authors suggest?
They point to distilling the test time gains back into the base models to reduce cost, exploring evaluator-light regimes by combining language feedback with smaller amounts of ground truth measurement, and integrating discovered optimizations more directly into compilers and tooling.
Let me play back the big picture. AlphaEvolve evolves code under an automatic scoring function, and it has already produced a new matrix multiplication result, nudged forward several open math problems, and shipped measurable efficiency gains in production. It's not a general scientist, but it looks like a solid recipe whenever you can formalize what better means.
That's a fair summary. It's a pragmatic bridge between LLM creativity and the rigor needed for real discoveries and deployable improvements.
Great, thanks Sam, and thanks to everyone listening. If you want us to do a deeper dive on the math or on the scheduling heuristic, send us a note.
Thanks for tuning in. Until next time.